Please, stage is yours.
Okay, thank you very much, Marcel. My name is Hassan Zier. I'm working at the Photovoltaic Material and Devices Group, and together with my colleague, Dr. Patricio Manganiello, we are going to give a brief, let's say, lecture about activities that we're doing in our group, and also give some inputs as general concept for the photovoltaics. So the agenda for today, first I'm going to talk about our vision, our research lines, and also the facilities that we have in the PVMD group. And then I will talk about photovoltaics in general and introduce some concepts that could be useful for the case of this, let's say, course, and for you guys maybe as an input when you want to develop your ideas. And then I will discuss about some example projects that we are working on or we already worked on in the PVMD group, which are related to urban integration of photovoltaics. And then Patricio will introduce this new area of research with the name of photovoltaics, and also gives example projects and talk about the ideas related to photovoltaics. And at the end, we will be glad to have a, let's say, question and answer session. And while I'm talking, feel free to write your questions or your comments in the chat part. Either me or Patricio, we will take care of it. Okay, introduction to our group. We are located at the, as Marcel said, EV building, and out of 6 departments, we are in electrical sustainable energy department, which itself has 3 groups. One group is working on photovoltaic, which is us. The other one works on smart grid and new ways of electrification. And also the other group works on efficient ways for conversion of different types of electrical energy in terms of DC, AC conversion, etc. Okay, as a general vision, what we want to do is to transform from this infrastructure that is more or less the case in most of the countries for electrical grid to a better version. And in this current version, it's a monodirectional and centralized, which is basically or mainly powered by non-renewable energy sources. And what we are envisioning is some sort of this image that you see. And if for that, the energy would come from green energy sources like wind, solar, and also we can integrate, let's say, the concept of photovoltaics on various surfaces in this urban platform. And in this way, we can have a bidirectional and decentralized energy flow between the different parts of urban area. So as, let's say, one line, we want to deploy XIPV systems. I will talk about this term, providing green electricity for sustainable electrification of the society. And what we mean by XIPV system is basically integration of PV system into whatever possible surface that we have in urban areas. So for example, you know that we can add PV to the roofs, we can integrate PV to the facade, to the roof elements, we can integrate PV into urban environment, we can also add or integrate PV into the environment, we can integrate it to products, and also we can use it in e-mobility, for example, integrated into the surface of this of the roads, or integrated to a vehicle. So in this way, we say, okay, we can integrate it potentially on every possible surface. So let's call it X integrated PV system, which enables us to give electricity to let's say, urban users. We can also provide power to industrial processes, give power to electrical cores or solar cores, or smart houses, and also see what impact we are making on the current infrastructure of the grids. So for that, we start from, let's say, upstream, which is for us high efficiency tandem PV cells. And based on these cells, we make PV-based intelligent energy agents that are not just a PV module, but also let's say, a surface that can not only produce electricity, but also can be used for sensoristic, and also to be used to assess the performance of its own and make it efficient as possible. So bringing on intelligence to these PV devices makes possible to have this PV technology for as much as possible users. To do that, so this is the whole value chain. We start from the material and devices, and we move to let's say the PV system. For that, we start again with materials, then move to the make devices and PV modules, in-house made PV modules, and then we further continue to the PV systems. To do that, we have 5 main research areas: solar energy materials, then hybrid tandem devices, and further smart multifunctional modules. And eventually we use this new concept in XI PV system. All of these 4 areas are backed up with a modeling platform that we have that is basically trying to have a unified platform to model everything from the device level up to the PV system level. So in this way, we can also make models and run simulation on the PV systems that are not yet made, or the new idea. So in this way, we can, let's say, reduce our cost without and get the result that we want without the need for real installation. In terms of application, we can say that we are working in the wide range of, let's say, size and also power. And it could be from micrometers up to hundreds of meters. And in terms of power, it could be up to megawatts. And the topic, more or less, for this talk is about photovoltaics and urban energy, which are has a, let's say, higher size and also higher power. To be able to make devices, we have several facilities in our clean room, and in there we deposit, let's say, different layers of materials to make new configuration of the cells and to be able to test these new cell architectures to see how they would perform. And further, we have a module manufacturing room, in which we can cut the cells, do this PV cell stringing, and also make PV modules, laminate the PV modules. In this figure on the left side, you see this device with this green light, which is our laser cutter. The one on the right is the laminator, and we can make various sizes of PV modules or mini modules up to the size of 60 by 60 square centimeter, which is the maximum size of this laminator. So here you see an example of IBC-based PV module that we made in-house with a efficiency up to 21% for the active area, and we can use different types of cell technologies and also different way of lamination. We can have it in glass foil, and also foil to foil, and eventually we can also have them little up to a certain curvature flexible. Okay, and then further, we usually put these modules outside and keep them under monitoring to see how they would behave under real working condition. And we have a big, let's say, terrace on a thermal power plant located in the TEU campus, and we have different types of tracker, different types of sensor, irradiance sensor, temperature sensor, weather station, inverters, maximum power point trackers, albedo meters, Hori catchers, etc. And here in this slide, you see an image that a photo that we took from one of our trackers that has, let's say, 3 in-house made PV modules together with 1 commercial module on the right side. I will get back to this photo further on during the lecture when I want to talk about different projects that we are running. We are other, let's say, lab facilities. We have the PV lab. We collected data from e-bike charging station. We also have a PV system that powers up a small in-house appliances to see how we can give power efficiency to these appliances. We also work with the Green Village, with a couple of projects and etc. So to give a really quick introduction about the educational courses that we have 3 main courses for PV, which are PV Basic, PV Technologies, and PV Systems. And most of the students that are following the solar track, they would go through these 3 courses, and then depending on their, let's say, interest, they either pass a PV modeling course or a PV lab course, sometimes both. And depending on the, let's say, the type of, again, interest that they have, if they're more interested into developing new devices, they would enroll for PV processing course. And eventually we try to have, let's say, 3 types of specialization as the output: PV design engineer, PV field engineer, and PV process engineer, depending on the type of the courses that they pass. Okay, enough with our group. Let's jump into the photovoltaics and its, let's say, main concept. And I'm going to start with the solar cells and how to build up to a PV array. In a nutshell, a PV cell is basically a PN junction that has 2 electrodes on top and bottom. When it is radiated by sunlight, the pairs of electron holes get separated and they get collected in an external circuit. And the symbol on the right bottom side you see is usually a symbol that is used for PV cell in electrical single line diagrams. So we know how a, let's say, solar cell works. Now, if you put the various number of solar cells together in one, let's say, unit, they call it a PV module. And then if we put a couple of modules together, it's going to be a panel. It's just a matter of wording in the, let's say, research community and also in industrial community. So if you go to the market, they say, okay, I have 1 PV panel, and what they mean by panel is actually the PV module. And if you put the panels or modules in series, you would form a string, and then putting these strings in parallel would give you a PV array, which is a building block of big solar parks. Okay, a little about the technologies. There are different types of technologies of photovoltaic in the market. Let's say the biggest share is for crystalline silicon wafer-based PV modules, which are mostly in a firm rigid style, and they have the share of more than 92%. The rest of the market is for for the thin film modules, which can have different types of absorbers. For example, CIGS module, copper indium gallium selenide modules, cadmium telluride modules, dye synthesized modules, or organic PV modules. And they have, let's say, different efficiencies. Dye synthesized PV devices are basically formed by dye particles and titanium oxide particles together with an electrolyte and a anode and cathode, and they're basically, let's say, a bit different from conventional photovoltaic devices. They're basically photoelectrical, chemical devices. And if we, let's say, have a quick comparison, the different technologies have different efficiencies. Crystalline silicon, the one that has the highest share in the industry, has the highest efficiency as well, but the price is a little bit higher. The thin film technology has a lower efficiency, but can be made flexible. They're lightweight, and also they're more resilient to, let's say, temperature variation. And in terms of price, aesthetic and efficiency, okay, it depends on the case or the project or the idea that you have. You can select one of these technologies available in the market to give a, let's say, hint about the maximum efficiencies reached in the industry. The maximum lab efficiency for crystalline silicon is around 26-27%, but for example, for dye synthesized PV cells, it's less than 12%. So in this way, you can get an idea how these efficiencies are different per technology of the PV modules. And PV modules, of course, they come with different warranty schemes. They normally divided into the manufacturer divided into 2 or 3 parts, and most of them claim that the module has the lifetime of 20 up to 30 years, and at the end of this lifetime, they guarantee that they're gonna have 80% of their nominal power. As you can see, different products come with the different, let's say, claims of a lifetime. For example, here you see a PV module from First Solar, and then, as I said, different PV modules have different schemes. Here you see a PV module from Unisolar, which is basically a flexible PV module. They normally put it at the locations that, for example, the roof is flat, but it cannot handle too much of weight. And now let's have a quick review on the structure of the PV modules. So if you consider the PV module on the right side of this slide, and let's take a look at the cross section of this module on this red line, and then we would see, let's say, 3 cells that are interconnected using metallic bars that connects rear side of one cell to the front side of the other cell. And then we have a encapsulation that keeps the whole, let's say, arrangement of the cells mechanically firm, because the cells themselves are quite fragile because they're not that thick, normally in the range of, let's say, 200 micrometers. And then it also helps to, let's say, prevent moisture to ingress into the cell, and also helps against corrosion. Then further we have a aluminum frame. But if we look at it, let's say, a little bit more in detail, first we have the solar cells, then on top of it there is a glass, but between the cells and the glass, on top side and also bottom side, there are 2 EVA layers that make this sandwich out of the PV cell, and below that we have a Tedlar foil, and then an aluminum frame. And what they do when they laminate a PV module, they put the cells and put the EVA, basically more or less everything except for the aluminum frame, and they put it in the laminator. They increase the temperature. Of course, it depends on the recipe that they use, but it's in the range of 120 degrees, and that would melt down the EVA, and the EVA will fill in all the free or available spots in between the cells. And then they further increase the temperature up to 150 to have everything, including the glass laminated. So in this way, we can have the PV module laminated. And then if you flip a PV module on the back side, you would see the junction box. And if you remove the hood, you would see basically a number of bypass diodes that are there to prevent a hotspot effect on the PV cells. For this topic, Patricio will discuss in detail about it in terms of what electronics that they can put in the junction box, or what types of connection that they can make. Okay, about cell stringing, just a quick review. There are 3 types of cell stringing. the most conventional way is the front-back connecting, and then the newer version is a back-contacted solar cell and also monolithically integrated cells. To have a quick review, front-back contacted solar cells, they're basically in a way that, let's say, metallic busbars of one cell is connected to the rear side of the next cell. And in this way, the positive polarity of the first cell is connected to the negative polarity of the next cell. And these the small, narrow lines that you see are metallization, they call it fingers. And the whole structure is the term is etch-grid that they use in the industry. So this is the most used case in the PV industry. And now they can, so when you are able to put the cells in series connection or in any way connect the cells, then it's possible to come up with different number of cells in the module, which it's basically either 36, 60, 72, or 96 solar cells. And depending on how they're connected, you can come up with different values of voltage and current, and it should be related to the appliance that you want to connect the PV module to that. For example, for this module, it has 36 cells. It produces 5 amps for each cell, and the output is also 5 amps, and total voltage is 21.6 volts. And for the same module, if you want to, for any reason, if you need higher amount of current, you can double the current by putting them in, putting 2 strings in parallel. And in this way, you get the same power, but with a lower voltage and higher current. When you string the cells, then you can put all of them on one plate. And as we discussed, then you can put it in a laminator to have a module as one unit, as one block. So previously, all of these, let's say, steps were more or less manual, but now it's almost 100% via robots, and it's totally automated. You can check this link to get some, let's say, idea how they make the modules in big factories nowadays. Okay, the second type of connection, this type of connection might be useful for maybe for your project, because they also come with let's say, different visual feature. As you can see in the back contact solar cell, the cell in the middle, the cell visually is different. What they do in this technology, they make holes within the cell using laser beams, and then they start this metallization process. And this way they can get the contact, which was supposed to be on the front side, they can get that contact on the back side. So in this way, both positive and the negative polarities are on the back side. Then they can use a, let's say, so this is the cross section of this technology. They normally call it the emitter wrap through. And if you look at the front side of these type of cells, they are quite similar to the back side of a water lily. And one of the, let's say, technically good points is you would reduce the amount of metallic bars on front of the cell. That would increase the efficiency, because there will be less effect of shadowing, but by those metallic bars on the cell. And on the back side, they have a metallic copper-based back contacted sheet, which is quite similar to a, let's say, printed circuit board that have 2 separate areas of positive and negative polarities. And when you overlay the cell on these conductive sheets, then you can collect the electrons out of this cell when it's illuminated. Another technology related to back contact technology is the so-called IBC cells, interdigitated back contact cells. The plus and minus polarities for these type of cells are all at the back side, and there is some sort of fingers together, if you can see. Then from the front side, there is no cover caused by metallic busbars, and it's also visually appealing because the color is totally uniform on the front side. And another advantage of these type of cells is the way that they're interconnected. So if you check the image on the top right part, the type of connectors that they put is so-called butterfly connectors, that they're not 100% rigid. They are a bit flexible. So when the module faces temperature variation, it causes slight changes in the size, or cause the mechanical pressures. These connections helps the cells and also the module to have its own original, to keep its own original features. Another type of connection is like stringing is monolithic PV modules. The way that they're connected, if you look at the cell for a PV module which is upside down, first they have the glass, then they put the front contact, and then they cut it with laser beams, and then they deposit the absorber layer, and further they again put another hole in that, and then they put the back contact, and eventually they make another hole in that contact. Of course, because they're cutting different material at different stages, the type of the laser beam, of course, that they're using is different, but it enables the cells to convey the current in this way. So this technique is usually mostly used for thin film technologies, and at least from a distance, the module would look like quite uniform. And there are two sections, of course, connection widths and also cell widths, and the target is always to reduce the size of interconnection widths with respect to the cell size. Okay, a little bit of information about solar irradiance. This is the spectrum of a black body radiation with the temperature of 6,000 Kelvin, which is the temperature of the surface of the sun. And the type of the irradiation that reaches on the top side of the Earth's atmosphere looks like this graph. And there is an, let's say, rather important term in photovoltaic that we use. They call it air mass. And you would see in the data sheets that they say, okay, we tested the module in air mass 1.5, and which is basically considering the type of the spectrum that the sun ray would have when it passes through the atmosphere of the Earth with the zenith angle of 38.2. And the difference in terms of a spectrum is the difference between these two blue and red curves. So the blue curves is the type of the spectrum that they use to test the PV modules, which is more or less the available sunlight spectrum on the Earth's surface. And AM0 is the one that is received on the top side of the atmosphere. And these voids that you see, of course, is because of the presence of different types of molecules in the atmosphere, that they absorb or reflect some parts of the spectrum. There is a term equivalent sun hour that is used for quick calculation or back of the envelope calculation in photovoltaic systems. Different regions of the world has, let's say, different equivalent sun hours. For the Netherlands, it's around 2.7 hours. So it means that on average during a year, 2.7 fully sunny hours are available. And you can also get access to meteor data if you want to, again, do some sort of calculation related to your PV integrated design, depending on the geographical scope and also accuracy of the data. They are mainly categorized in 4 groups. the satellite data, software-based data, which can come from different softwares like PVGIS, Meteonorm, and you can also get data from KNMI. And further, let's say, even you can, if you have access to local measurement devices, you can get data from them as well. Another important, let's say, the issue is the position of the PV module with respect to this position of the sun, and there are 4 important terms: tilt of the PV module, azimuth angle of the PV module, altitude of the sun, and azimuth angle of the sun. So using these 4 let's say the information, you can calculate the angle that the sun rays are hitting the PV module. The irradiance itself has 3 components: the direct component that is coming directly from the sun to the PV module, the diffuse component, the type of the irradiance that is scattered by the clouds or the presence of atmosphere, and also the albedo component, which depends on the geometry and also the reflectivity of the environment. Direct component, it depends on the angle of the PV module and its position with respect to the sun. The diffuse component depends on how much of the sky is actually visible, using the term sky view factor. And the albedo component, as I said, depends on the geometry, reflectivity of the materials, and also light source features. In the simplest way, there is a relation between 1 minus sky view factor with the albedo component. So in general, just to remember, the irradiance itself has 3 types of components that make different, let's say, contribution when you put the modules in urban areas with respect to the case that you study modules in large PV plants. Shading and the skyline. Patricio is going to talk about it in detail, but what I can say is whatever you're trying to design, do your best to do not make shadow on the PV modules, because the ratio of the shadow is not proportional to the ratio of the power loss. So for example, if you make a shadow on 1 or 2 cells, you would probably lose the 1/3 of the power that a module can give. Another important thing is the horizon. So it's important to know where the sun is, whether it's blocked or not, and how much of the sky is visible. And they do this analysis using a HORI catcher, which is basically a camera placed upside down towards a dome, and by capturing the picture, the dome itself captures the horizon, and then they further process this image into different softwares. For example, Meteonorm, they process it and then make it a let's say landscape image, and then overlay the sun path for that specific location. Then they would know on which days the sun is blocked and how much irradiance the PV modules will receive. For the case of urban integration, this problem is quite complicated, because the horizon is most of the time is covered by surrounding objects. As you can see here in the center of the Delft, the horizon is covered by surrounding buildings, church, etc. And it's not always simply possible to go to that location and run a HORI catching test. So there are, let's say, other techniques, online techniques to obtain this sky view factor. For example, this is the case for the center of the Delft, that you can see how the horizon look like there. And then we can further process it to calculate the sky view factor, or also shading factor, depending on the horizon and the position of the sun. Just to give you 2 more examples for the TU campus. For example, in location 1 and 2 in this figure, if you run a HORI catcher test and also further process the image, you would get a circular processed images like the ones that you see on the left side. And then based on them, you can calculate the SVF factor. Okay, now let me give a couple of examples about the project that we are doing for urban integration of PV. First is PV passing cooling. So in general, the lower the temperature of the PV module, the higher the efficiency and the higher the lifetime of the PV module. First approach is we can put infrared filters on top of the PV modules that they can reflect back the type of the portion of solar spectrum that does not contribute to electricity production. Another approach is to put some sort of, let's say, heatsink at the backside of the PV module to increase the effect of convection and further cool down the PV module. Another approach is to use phase change materials. And in these couple of slides, I want to focus on phase change materials. They're basically type of materials that they absorb a lots of heat in the phase changing situation. So for example, if you put thermal energy into a phase change material, first the temperature increases, and then when the phase of the material, for example, from solid to liquid is changing, a huge amount of heat energy is absorbed. And then further after, when the phase has changed, then the temperature increases. So we can use this let's say, more or less simple fact to cool down the PV module. But the key point is to know what is the desired temperature range of the PV modules is, and how the phase change material would behave. So for example, there are the different phase change materials that you can see here, but the range that the PV module is functional in, or most of them are working in, is from 20 to 25 degrees up to 60 or 70 degrees. So the melting temperature of the phase change material should also be in this range. So one of the materials that our colleagues selected is based on salt hydrates, and it comes from the company OC Atorkis with specific, let's say, features. The temperature, melting temperature is 26, latent heat is 180 for 180 kilojoules per liter, and also with a thickness of 1 centimeter. So what they did is they did a test on a glass PV module. As you can see, the layers on the left, they have used this general structure of the PV module, but they added 2 PCMs at the back. And to be able to resemble, let's say, the effect of building integrated PV, they added an insulation layer at the back of one of those modules. So when you attach a PV module into a facade, it basically has a really low amount of convection at the back, and that's why they put an insulation layer at the back side of one of these tested modules to resemble this BIPV performance. Then they laminated the module using the facilities that I showed. And this is the image of that module. And then they put it at the monitoring station, and they kept monitoring. And the result is actually interesting. What they have observed is, for the case of freestanding PV modules, when you put PCM at the backside, actually they does not help, because especially for the case of Netherlands, which is quite windy, then the main effect of cooling down is the convection. So when we put a PCM at the backside, it prevents this convection mechanism and prevents the module to be cooled down enough with respect to a reference case. But for the BIPV system, the result was very promising. They have reached, for example, for this period of 1 day in July, they reached on average 6 degrees less temperature for the case that the BIPV module has PCM at the backside. Another related project that I can talk about is PV chimney. I believe maybe you or some of your colleague already knows about it, because it was a collaboration between Baukunde and EV faculty. It is basically a combination of a naturally ventilated facade with a BIPV, with a photovoltaic facade. What they did is they transformed a solar chimney to a PV chimney by having a set of PV modules connected to a facade, and in front of it having a layer of glass. Then they studied two types of layouts. The first one was only the facade and PV in front, and a certain depths of cavity. And then the other approach was to have another layer of glass in front of the PV module, and they tried to compare these two layouts for both heat and electricity production. They have also tested this idea on a real building, 4-level building in Amsterdam, which had the electricity demand of 3.5 megawatt hour per year for the household, and also the heating demand of 35 megawatt hour per year. And they have got such result that they said for both PV in front and PV in the middle of the facade and the glass layer, both of them can potentially provide the needed heat flow. But for the electricity, the one that had glass in front of it has a lower electricity production. But all in all, they have tried to optimize these cavity depths, and they reached to a value of 20 centimeters. So when you have a 20 centimeter of distance between the PV module and the facade behind it, it would work as the optimized case. Of course, the study that they did was for the ideal case, the case when there is a let's say shift between the solar irradiance and the time that ventilation or electricity is needed in the building would affect the result. They have also placed it on one of the buildings, I believe, that is already has won several prizes in some international competitions, and now the concept is under further development using photovoltaic thermal technologies, that they're putting tubes of water at the backside of the PV module as well, and now it's installed in the green village. Another thing is colored PV. So it could be interesting for you guys, and general idea is, okay, when you have a glass, the light passes through and reach the PV cell, but we can engineer that glass by depositing different layers of materials that they have different refraction indexes and also indices, and also extinction indices. And then we can have portion, let's say, of the light reflected, which could be our desired color, and the rest of them they will go through the glass and reach to the PV cell to produce electricity. So for this project, our colleagues they made several types of, let's say, color for the PV cells with different let's say the types of engineering and design. And for example, what they did was they have tried to put layers on top of the cell to be able to do two things. First, to filter out sorry, reflect back all the infrared irradiation that would help to cool down the module, and also to reflect back the part of the irradiance that they wanted to have it visual. So for example, if they want to see the module in a green color, then they should reflect the part of the irradiance which is in the range of 550 nanometers. And then they tested those modules, and the main result that they got was it's not a big, let's say, there is no big impact on the performance of the PV module when you try to make them colored using these filters on top of the glass. And they did also a comparison for different colors. What you can take out as a message from this slide is it's not a big issue to have colored PV modules. Of course, it's going to be more expensive, but in terms of losing efficiency, it's not as high as they say, if we manage to engineer the top part of the glass good enough. And of course, when you have colored PV modules, it's going to be really cool, and you can place it at various, let's say, projects to have more visually appealing surfaces in building skins. Okay, some example for PV in mobility application. I believe all of you have seen this e-bike charging station in the campus. Another example is bifacial PV module noise barriers that they can be placed alongside of highways to be multifunctional, to reduce the noise and also at the same time produce electricity. It's possible also to integrate the PV modules into roads and have this concept of solar roads. It looks really promising, although there are some, let's say, still mechanical and material related issues with this concept, but so far it has been really promising. And for that, we have done a study on different highways in the Netherlands, and we have considered the network of the highways in the Netherlands, and we calculated the total solar potential of the highways, considering all the horizon and the surroundings for each spot on the highways, and also we considered the effect of traffic for two of the highways, which were, I guess, A12 and A16. And the result was interesting that we can, if we can apply these solar roads to the whole network of the Netherlands, it's going to cover 4% of national electricity demand. Another project, as an example of environmental integrated PV, is a project that we work together with a waterschap Rivierland. The idea was, okay, there is a land shortage in the Netherlands, and at the same time, it should be used for agricultural purposes. But the good point is there are a big amount of shallow inland water areas in the Netherlands. So if we are somehow be able to develop new concept of the floating PV that are economically feasible enough, then we can use those areas to provide electricity for urban usages. For example, here you see a artificial pond that we have developed to new floating concept with that. At the beginning of this project, we had several concerns like, do we get enough reflection from the water? The systems must be able to make possible the mowing activities. Also about the cooling effect, can we get or use the water to cool down the modules? Should we put trackers, bifacial PV, monofacial PV, reflector, etc.? And at the end, we came up with these two a new design that the one on the right is being patented. And we have constructed these floating PV units, as you can see in these figures, as a few example of the stages of construction. And eventually this is the system that has been installed. As you can see, the system on the left can tumble to follow the sun using two pumps that are placed inside the island that pumps the water from one side to another. And then in this way, the island can turn and follow the sun. The one on the right is a so-called retractable system that you can put all the modules on one side of these four pillars, and then it would enable mowing activities at the same time. Some of them are equipped with the reflectors, some of the modules are bifacial, some of them are monofacial, and we kept monitoring them, and we still do the monitoring to see how they perform. There were several observations. For example, the heavy fouling by the birds, as you can see here in this photo, they're always more or less present there at the location. And this heavy fouling will cause a hotspot effect on the PV modules. So we have to take care of this as well. And in terms of yield prediction, the system that can follow the sun and has a bifacial PV module with reflector at the back can produce 18% more electricity with respect to a reference freestanding monofacial PV system. Okay, on a, let's say, broader scale, we are also working with the campus real estate to have a 3D PV potential map of TU Delft. And the main objective was to prioritize the buildings that are the, let's say, the best for PV installation. For that, we start with the LiDAR data points, and using these LiDAR data points, we combine it with the building footprints, and then we reconstruct a 3D model of the buildings in the TU campus. And further, we apply our DC yield prediction model into that 3D model of the campus. And at the end, we will get the PV potential map on the TU Delft. So what you can see in this slide is the building footprint of the EV faculty. And this is the geometrical data points that we get for the EV building. And then further we refine it to this image that you can see, and then even we can get rid of these let's say small bumps that are available in this 3D image. And our eventual let's say shape is something like this, which resembles the 3D image of the EV building. And having this, we can apply our irradiance and DC yield modeling approach to see which part of the EV building is the best to put the PV modules. For example, this white part that you see is the best spot to put PV modules, and they're actually the PV system already installed at that spot. So what we are going to do in this project is to continue with the same approach for the rest of the buildings in the campus. One level higher in terms of application, we can also study the effect of PV installation on the grid. So if we put a lot of PV on the roofs, we have to make sure that whether the grid can handle that much of power in terms of voltage profile, in terms of total harmonic distortion, in terms of short circuit capacity, etc. So we started a project with the AMS Institute, Amsterdam Metropolitan Solution, that we want to study one region in south side of the Amsterdam to see how the effect of 100% PV penetration would be. So this is the part of the region, the pipe in Amsterdam, and we use the same idea of LiDAR data, and we get that data, we refine it further to reconstruct the 3D environment, and then we apply our DCL modeling together with the panel fitting algorithm to see on which roofs we can actually put PV. And then we study the effect of injecting that power to the grid on the low voltage grid infrastructure. This is a 3D image of the pipe area. As you can see, the red and blue lines show the low voltage grid lines that we studied the effect on them. For example, here this is a 2D image of the pipe that shows which buildings have how much PV potential, and what happens if we put or use all the potential of those buildings for PV installation. And if we do that, in some cases we would face, for example, voltage problems, as you can see in this figure. So the parts that are dark red, they would violate the low voltage grid regulation by having more than 10% of the per unit voltage. There were also other projects in our group related to product integrated PV. For example, you can see different stages of infotainment spot, PV powered infotainment spot. That is basically a place that we put a curved PV module to provide power for charging phones, or to have, for example, one tablet running to give information to the people in the city. This is also an interesting concept. This is a PDLC concept, polymer dispersed liquid crystal, which is used to have, let's say, a tunable curtains. So if you use, for example, PV power to power up these material, then we can tune the transparency of these materials. For example, the one on the left is less transparent with respect to the one on the right, and we can use cut cells, as you can see in this image, that are quite nicely placed, and they have the two functionality of being aesthetically more or less appealing, and at the same time providing power for this PDLC material to work as a tunable transparent coating. And there are several other projects that either I believe most of them I have talked about, and the rest Patricio will further talk about them. And this slide, you can also use it maybe for if you want some general information or textbook or scientific papers. We have put some links that can be useful to get information about PV while you're having your idea developed. And also at the beginning of each blue slide, we have put one link that you can use again for YouTube videos or further information related to that part of the talk. Thank you for bearing me for more or less 1 hour, and it was quite a number of slides. Thanks a lot. Now I think Patricio has some slides to present.
Ihsan, thank you very much already. We will also share the lecture later with our students.
Yes, sure.
Thanks for that. I would say 5-minute break for our students to have a short break. I need to go to the toilet, honestly. And we will be back at, let's say,